Thanks to boot.dev for sponsoring this video. In old Minecraft, items were extremely laggy, so the developers added an optimization. A small, very boring performance fix. One that would, completely by accident, become the foundation of Minecraft's most powerful communication technology. It's absurdly versatile. You can make an extremely complex network card, or a simple control for your mob switch. It can be 5 blocks away, or on the other corner of the world. And there's even a way to integrate it with cannons to track players, find bases, and even create block-by-block scans of terrain. But how did this all come to be? And how is it even useful in such a way? Now, one of the most frequent questions in the comments of my last video was how I even come up with all of these crazy redstone concepts. Truthfully, it comes almost entirely down to just knowledge and experience, mostly in computer science, as while redstone and programming are different formats, they follow the same fundamental rules. I take the same approach when developing redstone projects as I do when writing code. I learned programming from YouTube years ago, the digital equivalent of reading a book, as it didn't teach me how to build a project, or even how to really think like a programmer, just the syntax. Watching videos and reading about computer science will only get you so far. That's where boot.dev comes in. I tried a course on their website to brush up on my Python, and it's night and day compared to the old way. Let me tell you, I wish I had this back then. Tasks are interactive, and there are many tools to nudge you in the right direction without giving you the answer. There's an ever-expanding list of courses, from the basics of programming to learning how to create large-scale projects and even how to get a job in computer science. Use code IPLAYGAMES at checkout using the link in the description, or scan this QR code to get 25% off your entire first year on boot.dev. With that out of the way, let us return to the wireless. In 1.14 pre-release 1, item physics were changed. See, the laggiest case for these items was when they're set on a block, and that block is removed, so all of the items set on top begin processing physics at once. This was therefore changed so that the items, instead of falling in one group, fall in 4 groups, each separated by a game tick. And, as it happens, the way that these groups are calculated is extremely beneficial to us. They use the entity ID of the item, which is affected by other items. Importantly, it's also affected by every other entity in the world. So, if a goat spawns before that item is created, it will increment the ID it gets, hence it will change the group it's in. There are a lot of things that affect these IDs, so we cannot predictably tell which ID we're gonna get for a specific item. For example, sand falling or players logging on. To understand why, despite all of these negatives, this is still extremely useful for wireless communication, we must look at how the IDs play into this. What the code effectively does is that it takes the ID of the item and it applies the modulo operator to it, basically dividing the number by 4 and giving the remainder, which gives us either 0, 1, 2, or 3, which separates it into the 4 groups. From this, we can tell it's impossible to predict what specific group an item will be in when we create it, because any amount of IDs could have existed before it, meaning it could be literally in any group. But herein lies the trick. While we can't tell which group a specific item will be in, we can tell what the difference between 2 items will be. So if one will be in the first group, and we know no entities are created between them, we know that the next one will be in the second group. So we can tell if data was transmitted by comparing these 2 entities and detecting if another was created between them, which would be the transmission entity. To recap, when you make a single item, you don't know its group. But when you create multiple in a precisely controlled environment, you know what the difference you expect from them will be. Now you might say that that's really easy, just drop 2 items and check if the items are dropped 2 game ticks apart. And while this does work, it doesn't work in every case, as there is a problem. If we, for example, look at the case where the first item is in the 3rd or the 4th group, the groups for the 2nd or 3rd item afterwards weirdly loop around. Clearly, we need a better way to interpret these group differences, a wireless protocol. So, If we drop an item, then drop 3 more junk items, and then another item, we know that the first and the last item will always be in the same group, unless something else happens between them. This already brings us to an extremely simple receiver. Simply have this set up, and then another transmission item that can or cannot be dropped in between, and if the 2 items we're measuring are not synchronized, that means something was transmitted between them. Taking a look at an actual application of this in-game, we can see some irregularities. Firstly, we don't recycle the items. This is simply because it's easier to show this way. Second, we'll see that we actually drop the items that we're checking onto trapdoors before dropping them. This is important because for the code that we looked at to actually come into effect, they have to be stationary and sitting on a block. We'll also see that the priorities are actually encoded in an order so that they're actually separated by ticks. So this has the least delay, then those have a little bit more delay, and finally we create the last item. This is not ideal, and we'll fix this later for obvious reasons. If we activate this, we'll notice that nothing happens because the circuit here checks if the 2 signals from the 2 items are synchronized and cancels them out. But if we create an extra group of delay between them, this activates. Now, if you're following along at home, this is very important. The order that these repeaters are in has to be upkept so that the earlier created item is the one locking the other's output. Now, as great as this is, it's not exactly wireless, is it? The 2 inputs still require the same signal to synchronize them. How can we fix this? And to synchronize these signals, we'll use something very primitive, but in a bit of an unintuitive way, the daylight sensor. Now, you could just have 2 daylight sensors and use weather change or time of day change to synchronize 2 clocks and then separate them from the sensor. But there's an even simpler and even better way to do this that is controllable at any time of day. See, because of the way the daylight sensors are coded, you can actually update them manually, and this will synchronize you to a 1-second interval because they can only update every second. And while you can use one daylight sensor and just have it pulse around and update its own top every time it activates, this is not very clean. So instead of this, we use a 2 daylight sensor setup where one has the idle daylight and the other one has the modified daylight, and they subtract. Then as output, you have a piston that either blocks or doesn't block the system. Like this, to stop the clock, you can just set it in one case. For example, by simply powering the piston that activates the whole thing. This makes the clock stateless, and it is no longer pulse-based. And with a relatively simple setup like this, where we have a clock for the receiver and one for the transmitter, we can finally break this line, and this system will still work. If we turn this on, the receiver clocks every second, so it repeatedly performs this measurement. And turning on the transmitter, at first nothing will happen because we haven't enabled it, but then we can transmit a 1. I've gone ahead and taken the liberties to add item recycling. In this case, this is quite simple, just a few dropper loops to recycle the items that we use. Importantly, this works over any distance, at any time of day, so long as it's in the same dimension. Importantly, these daylight sensors also have to be unobstructed from above. And here we can see a very obvious problem. Because the creation of these items is separated by ticks, we can simply by accident create an item, or something else can, in the wrong time so that it transmits to this device. So if I just spam items here, we'll see that that receives, despite the transmitter not being active. Now, the obvious solution to this interference is simply to decrease the gap between the items being created, since there's simply a smaller window for other stuff to happen in between the 2 items. Not only can this be pushed to the same tick, but even to one tiny segment of that tick. Basically, it's possible to pick a very precise segment of a specific tick to create those items in. And because of how the game processes entity creation, it basically becomes completely impossible for a player dropping an item to interfere with these item groups. This is possible because the game processes different things in steps, and we can do this entirely in a single step of the game loop, the tile tick phase. In short, the game always processes player input in a different part of the tick. How tile-tick scheduling works is in-depth explained in my dedicated video on the topic, but I'll try to summarize what's necessary here. In short, some Redstone components don't activate instantly. Instead, they schedule their activation for a set number of ticks in the future. These components are called tile-tick components. For example, when a repeater receives a signal, it schedules itself to activate 2 ticks later, and at that point, it fires during the tile-tick phase. Components that work this way include observers, repeaters, comparators, droppers, and even liquids and falling blocks. There is a lot of nuance to this, but all we need to know is that within that tick phase, repeaters and comparators have a set order that they activate in. So repeaters will always activate before comparators in that tick phase. Here we can tell the order that the pistons activate in because the first one to activate will block the other one. So if we wanted to create 2 items in a specific order in the same tick phase, we could just use a comparator and a repeater for the 2 different priorities. But this becomes kind of problematic when you want to create more than 2 items in a specific order. Thankfully, there is another property of tile-tick components that is extremely helpful here. See, if we take 2 components with the same priority, for example 2 repeaters, and we schedule them in a specific order, they will also execute in that order when they activate. So even though the final layer has 2 components of the same priority, we can order them in a specific order anyway. And this is repeatable with comparators and repeaters on each layer. In fact, each additional layer doubles the amount of combinations that we have. Those of you that are a bit more computationally inclined might notice a pattern that is quite familiar: binary counting. In fact, the binary number tells you the exact position that this combination holds in the whole set. The signals produced from these numbers will always be in order. The reason that this pattern emerges is because Minecraft accidentally performs a type of sorting algorithm when sorting these priorities. It's called List Significant Bit, or LSB radix sort. You can look it up. I won't be explaining it here because it's far too technical. All you need to know is that this does result in the binary numbers being sorted. And here we can see a 2-bit tile set applied in game. With 2 bits you can create 4 combinations, so this uses all of it. First we create 1 measurement item, then we create the 3 padding items, then the transmission item, and then the last measurement item. So 0, 1, 2, and 3 in binary. You could make the transmission item of the same priority as the padding items, but that is kind of harder to see, so I made it a little bit spread out. You might have also noticed a small modification, that being that there's no signal specifically to power the trapdoors, because we reuse the same signal that activates the droppers to power the trapdoors for the previous cycle of items. This works out perfectly because there are 4 groups, and droppers have 4 game ticks of delay, so the signal is just extended to be 4 game ticks. We couldn't do this before because the repeaters were changing the timings of the signal. And trying it out, we can obviously transmit as normal. But this time, if I spam items, nothing happens. And this completely prevents interference from non-Redstone means, but Redstone can still interfere with it. A very simple example being a chicken farm. Taking a look at this chicken farm designed by the YouTube creator Writeup, it clearly becomes obvious why this happens. Also, there's a small bug here I'm gonna real quick fix. If there are too many eggs in here, this could get stuck on. Anyway, because of the tile set here being used to activate this dispenser, that is equivalent to a transmitter with this combination of components. And there is a bit of another problem as well. Now, we kind of sidestepped this earlier, but there are actually other Redstone components than repeaters and comparators. Taking a look at this 4-bit tile set, and this is true for any amount of bits, there is a repeater and a comparator at the end, at this point specifically. So anything that schedules this repeater later, or schedules this comparator earlier than 3 repeaters or 3 comparators, will have an item created in between these 2 components. And this is an example of a circuit that will interfere with that. Because an observer in this case has a lower priority than this comparator, it will schedule the repeater earlier than this one is scheduled, which means it'll go in between these 2. And the crazy thing is, this doesn't have to even align with the clock if there's any kind of randomness in its timing. If there's just like a clock here going, that will eventually synchronize and interfere with that tile set. So imagine we had a dropper right here, and this had a bunch of items in them. This could be a chicken farm, it could be whatever really, and that will interfere with basically every tile set possible with the current knowledge. An actual example of this problem in application is on Chronostasis V1. They did fix this on the second version, but it was quite problematic, as this design for the receiver, which it's a bit complicated, we'll get to this later, had an interference problem where there was a comparator and a repeater at the end. And these two components could get interfered between with a simple circuit as I showed before, and this did actually happen. The simple tidbit of knowledge that allows us to fix this is knowing that sure, we might be able to get a signal even by accident between a specific repeater and a specific comparator, but this is basically impossible between two components of the same kind. And we already saw an example of this on our previous tile set, as there is a very good reason that the interference happened between the part where there's a comparator and a repeater at the end. This interference can happen anywhere, but if it happens in a part where there are two components of the same type, it has to have happened a step earlier, and then those components just have to be the same on the circuit that activated it. And here is an example of how that can be simply applied to prevent interference. We just add two components at the end that thin out the priorities basically. These could be any two components, it could be repeaters on different timings, it could be observers, but for simplicity's sake, let's say they're still binary. So comparators for 1 and repeaters for 0. And here that is, very simply just adding the two repeaters at the end of the receiver and the transmitter, and this does still let them transmit normally, as I'll prove here. But this completely, well, almost completely, solves the problem with interference from other Redstone components. Of course, you can still accidentally build a transmitter-like structure. The next thing we'll try to tackle are these three droppers right here, because it's actually not necessary to create 3 extra items, we just have to rework the receiver a little bit. To explore how we could optimize this wireless design, we must first talk about wireless protocols. What a wireless protocol effectively is the arrangement of items that you use to achieve your desired effect, and then also how you interpret those items to receive data. For example, the arrangement that we currently use was invented by the original inventor of wireless redstone, to know to name. We call it M4IP, Modulo 4 Inequality Protocol. It works by detecting if the two items are not equal, hence the inequality in the name. Now, each different protocol has different perks and behaviors, the perk of this one being that it's extremely simple to understand, but it's not extremely efficient. And while it is nice to know conceptually what the protocol does, it's also very good to have a way to visually display all of the interactions between the items. So I set up this little diagram over here. We've used similar diagrams before in the development of protocols, but it is often not sufficient. For example, here we have at the bottom the arrangement of the items without transmission and with transmission. So this would be the first item that we measure. These 3 would be the padding items, and this would be the last item that we measure. And then here we have the transmission item just spreading it out by 1 additional point. And here we have a diagram that shows us the 4 groups and how the items basically interact with them. So we have the 4 possible starting positions, and each one of these is one of the possible conditions that the device could find itself in depending on which group the item is in. So if we create an item and it's in the first group, then we create 3 more padding items. Then the next item, when it wraps around, will be in the same group. And this is true for all of these cases, basically. And if we have a transmission, they will get mismatched by 1. So it could be first group, second group, third group, fourth group, or fourth group, and first group, and loop around again. And that's all fine and dandy for a protocol we already know the functionality of. Obviously, we know we can just check if the items mismatch and then receive. But what if we want to go from an arrangement of items back to a protocol? To know, hey, this is how we want the items to be, how do we interpret these items? Well, here I've made an example where I have only 1 item for each measurement, no padding items, and a transmission item in between. This is basically as simple as you're going to get for a simple one-to-one connection. So, what pattern can we see here? Well, first, let's look at the first one. So, if the 2 items are 1 group apart, they can either be in 1 group difference, or they can be in the last and in the first group. If they have a padding item, however, a very interesting pattern emerges here. So if we look at it from sort of a surface level view, we can notice that every single time in each of these cases, both of the measured items are exactly 2 groups apart. So this could possibly be useful to us. But how? To understand why this knowledge is useful, we also have to note that they are never 2 groups apart in the original version without the extra transmission item. So if we have a system that's able to determine, hey, these are exactly 2 groups apart, then we can successfully determine that we have transmitted with only 3 items created. In practical Redstone, what this effectively means is that we have 2 lines from the 2 inputs from the 2 items that we measured, and we want to detect if they are exactly 2 game ticks apart. Now, you might think, hey, you can just delay 1 by 2 game ticks and check if they're synchronized, right? But think again, because you don't know which one actually goes first. But indeed, there is a better approach, this one figured out by Avalon. So if you take each of these signals measured from the items and you expand them into a 2 game tick pulse, you'll get these interesting patterns. In the standard version, if you combine them, the 2 game tick pulses will either create a 3 game tick pulse, or 2 separate 2 game tick pulses. But in this neat arrangement, where they're always 2 groups apart, it will always combine into a 4 game tick pulse. So if we combine them, all we need to do is check if the result is 4 game ticks long. So here we have our receiver and transmitter creating all of the items in the correct order. And we know that this signal will be exactly 4 game ticks long, no longer or no shorter, when the transmitter is active. So how do we check it? A very simple way to check it would be to invert it and send it through a 4 game tick repeater. This repeater will only turn off if it doesn't receive a signal for 4 game ticks. So then we can uninvert it again, and this should work. So if I go and transmit, that goes and activates. Now, as it happens, a redstone lamp also needs 4 game ticks to turn off. It doesn't turn off visually, but if we check here, it does actually produce a pulse. So we can use a redstone lamp instead of this repeater and take an observer output. And this is basically as simple as such a circuit can get. By the way, this specific protocol is called M4GP, or the Modulo 4 GAP protocol. All of these protocols are archived in our Discord server, TickLink. Okay, so let's talk about throughput. Here I've put 2 receiver bits and 2 transmitter bits in parallel in the same clock, but with different prefixes on this tile set here. So they're basically 2 separate receivers that happen in different parts of the tile set. And you can easily do this. So here, this one activates between these 2, and it transmits there. I can also transmit to the other one, and it activates between these 2, and even to both at once. And as I can change if I transmit or not once a second, this transmits 2 bits a second, and it is expandable however much I want. I could even treat this as 2 separate receivers and have them have separate clocks and put them in separate locations. And this works completely fine, but there are better ways to do this, and this will be explored in the second part of the series. For now, let's ask ourselves what these 2 items here are doing, because, as we'll soon find out, they are actually doing basically the same task. So this first item creates a reference point at the end, which means it tells you which item is after you're supposed to receive. And this one tells you which item is at the start of the next transmission / receiving pair. So you could use the ending point of the previous transmission to receive for the next one. So we can basically reuse the item both as the ending point of the previous bit and the starting point of the next, and receive a bit between each of these items like this. And there is actually one more thing we can optimize in how these components down here are encoded. If we check, the transmitter always has a comparator at the start and the receiver a repeater. This is because the transmitter is basically one after each receiver. So you have receiver, transmitter, receiver, transmitter, receiver, transmitter, receiver, transmitter, and you keep doing this for however many bits you have. which means that, for example, if we just have the transmitter have the same tile set, but it's always after the receiver tile set, that works completely fine. So for example, we can use one component to encode that difference for the whole transmitter, and one component to encode that difference for the whole receiver. Basically what we've done here is we've taken that least significant bit, because it's the same for the whole device, and just made it appear only once. Now, you might have been looking at this design for a while, and also the transmitter, and thinking, hey, can't we just squeeze that together? There's all of this air here, right? And there are a couple problems with that, but that is actually possible, easily so for the transmitter. And indeed, that can trivially be done. For the transmitter, basically everything can just be squeezed except for this last part, because they would power each other diagonally. So you have to have this set up where it powers this dropper and then the other one via quasi-connectivity. Basically all that means is that this can power both of the droppers basically. Now for the receiver, everything tiles completely normally, because here we have those trapdoors for separating them and also for landing the items. But how we compare the signals is still a bit of a question. See, the trouble is that we have to compare each two adjacent signals. So not only do we have to compare these two, we also have to compare these two. Because the middle one has to compare with both of them, that becomes kind of problematic to do in a one-wide tileable fashion. Ultimately, the solution here ended up being to simply split the signals into two parts, and to have a system like this, where it uses a trapdoor and a glass pane to split the signal up into its own lane and into the next lane over. Of course, the first one doesn't have a comparison before it to compare with, so we still get 2 bits out. So I've gone ahead and expanded these to be 6-bit receiver and transmitter, and I've also removed that block here. That was only to space out the extra repeaters from the rest of the tiles in. So if you don't need the visual aid, you can get rid of it. And as we'll see, this works completely normally, except it's way better because it's more compact. So if I transmit, let's say for example I want to transmit a little checkerboard pattern, and it gets received. And this gives us a throughput of 6 bits a second. A really important thing here is that I had to change it out for unstackables, because if they're stackable, they will actually stack between the segments. Now, this specific receiver is called the CTR, or the Compact Tileable Receiver. Yeah, we're not very good with names. But it is actually possible to make it more compact, though it requires knowledge from future episodes of this series that, well, we will eventually get to. It's a bit complicated. Just know that it's possible. And while that does wrap up this episode of the Wireless Masterclass, be sure to subscribe, because in the following episodes of it, we will explore way more that you can do with wireless Redstone. For example, how to dynamically reconnect these devices with Redstone. So for example, you can have multiple receivers and you can say, hey, transmit to this one, and then after that go to that one. Or you can even have a radio-like system where multiple receivers can listen to one transmitter and then change the radio station. A download to the designs used in this video has also been added to the description, right over to that line, which is what has been explained in this video. And as more of the episodes release, they will progressively add more and more depth and increase the distance of this line as we go through all of the designs that we've lined up. Now, I've also added a resource in the description, a playlist from my friend GiorgioJGZ, who has a short series that explains the basics of technical Minecraft, and he also recently explained basics of wireless in a couple of his shorts. And also a write-up from my friend Tangible for those of you that prefer to read about some of this wireless stuff, which is work in progress. And again, if you're interested in learning how to build bigger or technical projects, I cannot suggest boot.dev enough. Have a good day. Bye.